All right, so I'm Jeff Deppa. I'm from Rutgers University. And so basically I did the REU program this summer, which is a chance for undergraduates to get exposed to doing research. And my project was working with the private sector, Weather Decision Technologies. And they do a lot of wind forecasting for wind farms to understand how the power grid is going to be influenced by the source of energy that can fluctuate a lot more than, say, something that's controlled like coal or some other source. So it's a really big thing with renewable energy evolving, trying to get these forecasts down so that grid operators can understand how much power is going to be coming into the grid at any given time from a source from Mother Nature. So
what made you choose looking at this particular wind farm? The Blue Canyon Wind Farm is in Kansas, is it?
It's in southwestern Oklahoma. Yeah. It's a little southwest of Oklahoma City.
Yeah.
And so basically, the company, this is the biggest wind farm in Oklahoma. They have I'm not sure how many turbines now, about 300 or 400. And so talking about all these together, it's really a big player into the grid. How much power is going to be coming into the grid? So trying to understand ahead of time how much power output there's going to be from this particular wind farm is very important because it is the largest wind farm, and so Weather Decision Technology works with a lot of wind farms in Oklahoma, and this was kind of one case where I was seeing the model was making some errors. I was kind of curious about it. We had a chance to actually go to the Energy Corporation and talk with them, so it really kind of sparked my interest in this particular case. Kind of understand the meteorology and how the model resolved what was happening.
So how did you know the model was making errors? It was indicating more wind than was actually happening, or less?
Yeah. Well, basically, it pretty much never hits it dead on. Over the course, I was looking at nighttime from basically when the sun went down to when the sun came up, when the Southern Plains nocturnal low-level jet was strongest. And the cases I looked at most of the time, it was under forecasting the wind speed. So basically we can look at what the WRF model is putting out, and then this is the actual wind farm wind speeds. And you can see in this case we're talking about 1 to 2 meter per second difference for the majority of the night. And so that might not seem like a huge difference, but when you're actually the power equation it's a cubic relationship. So the difference between an 8 and 10 meter per second wind speed could lead to about a 50% power difference, and we were talking about hundreds of turbines. These are something grid operators really need to know about, in advance, so they can take the proper actions. So
what did you find? What's going on with the model that it's missing just a little bit? But I mean, is this unreasonable to expect the model to do better? Or?
Yeah, I mean, obviously, the better it can do it, the better it can resolve it. It's going to be just better for the wind power companies. I found it quite impressive coming into this, basically not even being exposed to this before this summer, and I was shocked that the model could even do this well. I'm like, wow, that's really impressive. But they really want to nail it down as best they can. And one thing I looked at is, this WRF model is on a 3-kilometer grid spacing. There are some terrain features in this area, and the terrain's not completely resolved. And so there is a bit of a wake effect that happens as the flow comes over the terrain. And the fact that we're talking about a low-level jet that has a huge shear within the first couple hundred meters off the ground, a little bit of error in how the model resolves the terrain and the flow over the terrain, and the stability in the boundary layer, that's going to lead to these errors. My hypothesis is that would lead to these types of errors that we're seeing, and that's kind of where my conclusion was heading, is that it's some of these mountains that are a little more intermittent and not as continuous. The model is not completely resolving correctly, and that could be where some of the flow errors.
You got a picture here of the site.
Right.
And I don't know if people see on video, but it's a little bit of a rise there. Not a huge rise, but
right.
A couple hundred meters at most?
Yeah, right. So where the picture's taken from is where the flow is initially coming over, and this is Mount Scott here. It raises over 300 meters from the valley elevation to the peak. And whereas the mountains behind that, it's about 150 meter rise. So we kind of looked at this and we did some of the, some kind of back of the envelope calculations with the mathematics and found, you're not going to have the type of wave flow that you would have, say, with flow coming over the Rockies, but it's enough that there's going to be some sort of effect. It's not going to go over this terrain and just be completely the way it was when it first encountered the terrain. So there's still, even though it's not going to be something that's going to be real substantial, it's enough to cause this even small error in the models that really leads to big power implications when you talk about this kind of cubic relation.
So at this resolution, the model is getting you a nice jet.
Right.
But it's not getting it vertically in the right place.
Right.
Horizontally, I mean, in terms of XY plane, it's showing you where pretty much the peaks are in the right places, but
right.
It's not vertically.
I mean, actually, in both directions, there is a bit of discrepancy. Part of it because these mountains are kind of, they're the ones where the flow's coming out of the south. The mountains are not continuous, so there's there in that direction. But generally, as with a lot of boundary layer problems with the models, there's definitely a vertical issue as well. But really, I would say it really is a combination of both. And finding out where this peak wind speeds occur, it seems like there's that on a kind of XY plane. There's definitely some error there as well.
Right, so what's a wind farm operator supposed to do with what you just have been telling us?
Right. I would say it's definitely important to definitely take these some of this data with a grain of salt, especially where we see some of this error continuously happening. But really, they have to be most concerned on nights when when the wind speed is in this 10 to 12 meter per second range, because that's when just a little fluctuation in wind speed will lead to a huge power output. So those are nights where they're going to want to be paying attention to the forecast a lot more, and really kind of looking at things on a more of a minute-to-minute basis. Whereas if the wind speeds, you don't have this nocturnal low level jet and things are a little calmer, then it's not as critical.
But at the same time, it sounds like you're also sending a message to the people who produce the forecast that a little bit of uncertainty information on how the model is able to capture these phenomena would also help the operators.
Right. Yeah. Absolutely. Understanding where that, not only where the range, when you give out a forecast, understanding where the kind of bottom and top end of that range, not just with the wind speed, but also with the power, because a 1 to 2 meter per second window with the wind speed, that could be a huge difference in terms of the power output, and there's just a lot of things to consider. They have to be aware that these models are, the wind turbines blades are, they're covering a swath that can be upwards of 100 meters. So, the model is trying to resolve these layers. The wind speed at the bottom of the turbine might be a lot lower, than the top with these shear with the jet. So, just understanding some of the intricacies that they're trying to predict is really important for not just the people that are making the forecast, but the end user too, to understand. For the best. Yeah,
Thanks
excellent.
A lot,
yeah, thanks.